Hi everybody, welcome back to the channel. In this video I want to take just a quick look at a few examples that use specifically the first part of the fundamental theorem of calculus. In the last video I actually gave you an example using the second part of the fundamental theorem of calculus, and there's a lot of application or examples of applications of that. But I wanted to make sure that I just include a few examples of applying the first part of the fundamental theorem of calculus. Okay, the first part also gets us to be able to use the second part as well, so it's really useful to have the first part so that we can also prove the second part like we did in the last video and then use that, and that's incredibly helpful. But there's also some applications and some specific examples that we're going to see that use the first part of the fundamental theorem of calculus as well. So let's look at just a couple of different, I think I'll have three different kinds of questions, or they're all the same kind of question, but they all have a little bit of a variant on them. And so three different specific examples here. So the first one we're going to look at says this: let's suppose that g of x is a function that looks like this. G of x looks like the integral from 1 to x of the square root of 1 plus t squared dt. Okay, and I want to remind you what the fundamental theorem of calculus says. It says that if you have a function g that's written as an integral, and you have a bound on that integral that is an x, that's your variable. We used a different variable inside. We used a t inside. And what we said is that basically if you go find the derivative of g, the derivative and the integral should sort of just cancel each other out, and you get f of x. Now notice it didn't say that you get f of t, it said you get f of x. So this is a function that we're starting with. The directions on this specific problem will say something like this: find g prime of x. Okay, now what a lot of students want to do when they see a problem like this is they want to somehow take this and you see something with a square root and then a 1 plus t squared, and a lot of students want to start to take the derivative of this whole thing over here, and it's not a bad thought, but it's not exactly what we want, because remember, g is not just the square root of 1 plus t squared. G of x is actually the function that looks like the integral from 1 to x of that function. So g of x is not that function. That function is actually this function over here, which is f of t. So we're not saying that g of x is f of t, or even that g of t is f of t. It's not. G of x is some function that's defined as the area under the curve from 1 up to x of that. But so fortunately, we don't actually have to go take the derivative of something here with a square root in it. Really, what the fundamental theorem of calculus part 1 gives us is that all we need to look at is if you have an x as your bound, then what ends up happening is that g prime of x is supposed to just be equal to f of x. Well, remember what f of x is. F of x is the function that's inside, is the square root is f of t. So basically it says take that function that you had inside, and the derivative and the integral should sort of cancel each other out, but you don't get f of t as your answer. You end up getting f of x as your answer. You actually don't need to do a lot of work for this problem. You end up getting 1 plus, just replace the t up here with an x, you end up getting 1 plus x squared. Okay, I see a lot of students in problems like this try to want to make this a ton of work and want to take it and take a chain rule in here and take a derivative, but because the fundamental theorem says, hey, when you have g that's defined as an integral, just go ahead and the derivative of the integral kind of undo each other, but you just got to be a little bit careful of what your bounds are. So g prime actually just looks like this right here, and that's about all the work that is needed is really just to recognize that your inside function is f of t over here is the square root of 1 plus t squared, and all you need to do is replace the t with an x because the x is what you have on your bound. Okay, so the fundamental theorem makes this problem a whole lot easier, where you don't need to actually take the derivative of a function by using any kind of a rule or a chain rule or anything like that. Okay, let's modify just a little bit. we're going to have the same directions. The directions are going to say something like find g prime, no, they're going to say find g prime of x, okay, and here's the g function that we're going to be given. It's going to look really, really similar. It's going to, I'm going to change it just a little bit though, okay. So this time, instead of the integral going from 1 to x, now the integral is going to go from x to 1 of the square root of, I'll just leave it the same, I guess, 1 plus t squared dt. Okay, so really the only thing I've done to change this problem from the last one is that I just switched these bounds. Okay, now when I say it like that, you should probably have an idea, a little bit of an idea of what to do with this, or an integral rule that we used in one of the past videos. Okay, there was a rule in the past video that said something like this, that if you have the integral from a to b of f of x dx, this is actually equal to, it's almost equal to the integral from b to a of f of x dx. But what we said was that because the order of your interval or your endpoints is swapped, you're kind of going in the other direction. And every time we go in the other direction, we're actually going to throw a negative in there. And so we actually have it where if we swap the endpoints and turn them around and put them in the reverse order, that you don't get exactly the same thing, you get exactly the opposite of what you started with. Okay, so let's think about kind of what does that mean in this example right here. Let me go ahead and create a little space here. So think about what does that mean. Before we think about trying to take the derivative of g up here and use that fundamental theorem of calculus, what I would recommend is writing this integral in a different way so that we switch the bounds. What if it looked like 1 up to x instead of x up to 1 of the square root of 1 plus t squared dt? I think we can all agree this problem now would be exactly what we just had in the last example problem. But I can't just switch the bounds just like that. I have to switch the bounds and make it a negative. So there's got to be a negative out front. Okay, so what does g prime look like? Okay, g prime of x is almost exactly the same thing as the square root of 1 plus x squared, but now I need a negative on there. Okay, so it changes things just a little bit if our bounds are in the other order. So just want you to be careful about where your bounds are. What do your bounds look like? That's a really important thing for you to keep track of, and be aware of where is your variable on the bound, on the lower bound or the upper bound. Okay. In fact, we could actually have another problem. I told you there were going to be 3 examples. How about we look quickly at a fourth one? So here's another example. What if we have same directions in here? I'm going to say find g prime of x. And what if g, now, what if it looks like the integral from x to, I don't know, something like x plus 1 or something like that, okay? They'll just kind of pick a nice straightforward function, except it shouldn't have an x in it. Let's go ahead and use t. So how about t squared dt, something like this, okay? Again, same thing, we want to think about our integral rules. And what I would recommend is splitting up the integral when you know it goes from x to x plus 1. Now we have variables in 2 different spots. Well, this is equal to the integral from x to a constant. Pick a constant. How about, I'll just say to 1 of t squared dt. Now we do got to be careful about where this function is continuous. It's got to be continuous on the interval, but since I'm using t squared, that's continuous everywhere. And then plus the integral from 1 up to x plus 1 of t squared dt. And so now I could go ahead and think about using the fundamental theorem here in this part, and the bound looks like what we want, where we have a constant on the bottom and our variable up on the top. And then this one, I can switch this, the first one, I can switch these bounds here again by making it a negative out front, and then going from there. So this whole thing would end up looking something like this, where if you flipped them, it would be a negative not t squared, but negative x squared Okay, so there's your first one. It's not just an x squared, replace a t with an x. It's actually a negative x squared, so you flip the bounds. And then plus, the last one would look like x plus 1 squared. Okay, so that's what your g prime of x would look like. So you got to think about the bounds there that you have. All right, one last example. This kind of kicks us into that one last example. Notice how in this last one, we have x plus 1 as our bound. So it does bring up an interesting point. Like, what if you don't just have an x up in the bound? What if you have something that's a little bit more complicated? Okay, so let me use this example. So let's say we have same directions here. We're going to go ahead and find g prime of x. And in this case, we're going to say that g of x looks like the integral. I'm just using 1 as kind of a nice easy bound every time, but find the integral from 1 up to x to the 4th power of the secant of t dt. Okay, so in this problem, we could actually think about this x to the 4th up here and kind of think about this as almost a substitution, really. Let's use a different labeling here. Let's introduce a new variable. Let's call this u. And u is going to be equal to x to the 4th power. Okay, so what I want you to think about is there's actually going to be a chain rule here. Here's another way to write g of x. Okay, g of x looks like the integral from 1 up to u of the secant of t dt. And now if we use the fundamental theorem of calculus to find g prime of x, okay, which I guess it maybe really shouldn't be g prime of x in this case, it's more like that's g of u, I guess, where we replaced an x with a u in there. Okay, so we should think about kind of what we have here where we're looking at g of u. What we want to find is g prime of the original. So when we take g prime here, what we're going to actually have, g prime of x, is going to look like g prime of u, but then there's a chain rule. We need to also have u prime, or you could call it du dx if you want there. And so it's going to work exactly like we had in the other examples, where when we find g prime of x, it is just going to be, we are just going to be able to replace the t with what we have as our bound, and it's going to become a secant of x to the 4th power. There's your f function with u plugged back into t. We're using x to the 4th instead of u though, but then what we also need with this chain rule, we also need to multiply by u prime. So what is the derivative of u here? That's the derivative of x to the 4th. We need an extra 4x to the 3rd there because of that chain rule. So just be careful. If you have g of x defined as the integral from a constant up to a function up here, you can really think about, you can just plug in your bound in for t, but if that's a function and not just an x, you need to also multiply by the derivative of u there. So here's kind of another way to think about the whole thing, is to think about it like this, where this actually works when you just have an x up top, because then the derivative of x is just 1, so you're really just multiplying by 1. But if you're finding g prime of u here, then this looks like f of u times, you can call it du dx or call it u prime or whatever you want to call it. And so here's our f of u part up here, and then the 4x to the 3rd is our du dx. So just be careful if your bound is not just an x, if it's a little more involved, you do need to use a chain rule and have that other piece there on the end. Okay, so these are all the different, these are a handful, or I would say 4 different types of examples of stuff you could see that involves using the fundamental theorem part 1, and then we also have a lot of examples that we have seen and that we will be seeing that use the fundamental theorem of calculus part 2. All right, hope you enjoyed.